Hello and welcome. Have you ever looked at a robot arm and just wondered, how do we get a pile of metal and motors to move with such incredible precision, sometimes even with a sense of grace? Well, today, we're going to dive into exactly that. We're going to follow the journey of a robot as it learns to move, evolving from a blind, clumsy machine to one with a perfect touch.
So let's start with a really simple but totally fundamental question. You tell a robot arm to move exactly 10 centimeters. But what if something gets in the way? What happens when the messy, unpredictable real world interferes? Honestly, figuring this out is the first major hurdle for any robot that has to operate outside of a perfect, sterile lab.
And this problem brings us right to the most basic type of robot control out there. It's called open-loop control. It's simple, it's cheap, but it has one massive and sometimes pretty dangerous flaw.
Okay, so imagine telling a robot to do something and then just walking away and hoping for the best. That's open-loop control in a nutshell. The controller sends a command, and then that's it. It just assumes with total confidence that the command was carried out perfectly. There's zero feedback, zero confirmation.
Take a look at this paint sprayer example and focus on step 4. The system assumes it worked. Now, let's say the paint hose gets snagged on something. The controller sends out all the electrical pulses it thinks it needs to move 10 centimeters, but the arm only moves 5 before it gets stuck. Well, the controller has absolutely no idea. Its internal map of the world is now just wrong. It thinks it's at the 10 centimeter mark, but it's not. It's a complete leap of faith.
This is just a perfect way to think about it. The robot is basically blindfolded. It's just following orders, completely unaware of its surroundings. So if it hits a wall halfway, it'll just keep marching in place, totally convinced it reached its destination. You can see how its idea of where it is gets completely disconnected from the real world.
So that's the big question, right? How do we fix this? How do we give our blind robot some kind of sense, a pair of eyes, so it knows what's actually happening? Because if we can't solve this, our robot will never be reliable or safe.
And that leads us to the solution, which is an absolute game changer. We're going to introduce the concept of feedback. We are going to close the loop and give our robot the ability to sense its own actions.
And it all comes down to this really simple but powerful loop. Measure, compare, and correct. The robot is no longer just guessing. You see, we add a sensor, something like an optical encoder, right onto the motor. And that sensor is constantly reporting back to the controller, saying, hey, here's where I actually am. The controller then looks at that, compares it to where it wants to be, and if there's a difference, it fixes it on the fly.
This table just lays it all out, doesn't it? We go from a fire and forget system, which is fragile, to a trust but verify system, which is robust. So let's go back to our paint spraying robot. Now, with closed-loop control, if that hose gets snagged, the sensor screams, hey, we're stuck. The controller sees that error and can actually increase the power to the motor to push through the obstacle. It can fight back. It becomes an adaptive system.
All right, so problem solved, right? The robot now knows where it is, and it will always get to its target. But as always in engineering, you solve one problem and another one pops right up. Now the question is, how does it move smoothly? How do we keep it from being a violent, shaky mess that just destroys itself?
This is where we get into the actual brains of the operation, the control algorithms. And to make this super clear, let's use a cool analogy, a delivery drone that's trying to land perfectly on a small balcony. Okay, the simplest approach is called proportional control, or P control. The logic is simple. The control signal is proportional to the error. In other words, the further away the drone is from the balcony, the faster its motors spin. Makes sense, right? But the problem is momentum. As it gets close, it's still going way too fast, and it overshoots the target. Then it tries to correct and overshoots in the other direction. It ends up just wobbling back and forth like an enthusiastic rookie pilot who's all gas and no brakes.
So how do we fix this? We add a D for derivative control. Now, don't let the math term scare you. All derivative means here is the rate of change. So this part of the algorithm is just looking at the drone's speed. It's like a cautious veteran co-pilot. It sees how fast the drone is approaching and thinks, whoa, whoa, slow down, we're coming in way too hot. It applies a braking force that's proportional to the speed, effectively damping out the P controller's wild enthusiasm. And the result? A beautiful, perfect, smooth landing.
Okay, but what if there's a constant nagging force, like a steady wind pushing down on our drone? A PD controller might get it to hover just an inch below the balcony, stuck in a sort of stalemate. This is where the I for integral control comes in. The integral term is like the robot's memory. It accumulates the error over time. It sees this tiny, persistent error and says, you know what, we've been off by a little bit for way too long. It then slowly but surely ramps up the power until it overcomes that wind and nails the landing perfectly. By the way, this PID logic is the secret sauce in everything, from your car's cruise control to the thermostat in your house.
Okay, so our robot is now a master of movement. It's fast, it's smooth, it's incredibly precise, as long as it's just moving through empty air. But let's be real, we want robots to actually do stuff, to interact with the world, and that means touching things. This brings us to the final, and maybe the most fascinating upgrade. See, up until now, everything we've talked about has been about telling the robot where to go. That's all position control. But now we have to teach it something totally new, how hard to push. Welcome to the world of force control.
This quote about shaking hands just nails it. Think about it. If a robot's only mission is to get to an exact coordinate in space, it has zero regard for what's already there. So if you tell it to move to a point inside someone's hand, it will either stop short in the air, or it will use its maximum power to try and get there, crushing the hand in the process. A robot that only cares about position is a menace when it needs to make contact.
So what's the solution? Well, it's actually really clever. You don't pick one or the other. You use both at the same time. It's called hybrid force control. Let's go with the window wiping example. Moving up and down and side to side along the glass, that's all precise position control. But in the direction pushing into the glass, that's where it switches to force control. It's programmed to maintain a constant, gentle pressure, ensuring it cleans effectively without, shattering the window.
So what we've really been doing this whole time is building a toolkit, and this chart really summarizes the whole journey. Each one of these control strategies is the right tool for a specific job. You've got the dead simple fire and forget open loop, which is perfect for something like a 3D printer. You've got high-speed, smooth PD control for most industrial arms, all the way up to hybrid force control for delicate tasks that need a sense of touch, like polishing a car or carefully grinding a surface.
So when you step back, it's a pretty amazing progression, isn't it? We started with a blind machine that was just guessing. We gave it eyes so it could see where it was. Then we gave it coordination so it could move gracefully. And finally, we gave it a sense of touch. It just makes you wonder, what comes next? What's the next human sense we're going to figure out how to engineer into these incredible machines?